Good morning, everybody. I thought we'd have some fun this morning. Normally, Keynote's on technical, but I'm going to break that this morning. We're going to do some live coding. We're going to look at some of the trace tooling. We'll play around a little bit with that. You'll see some of that. Everything that I'm going to show you is up on that GitHub repo under Arden Lab. So after the talk, if you're having trouble finding it, just grab me. I also will not be taking questions after. So if you have questions, write them down, and then you can find me. And I'll be more than glad to talk to you, okay? We only have 45 minutes. I know that sounds like a long time, but I'm going to need every single minute. So stop slacking. I got to get going here. Now, here we go. Let's get into our code base. So here's the idea. I wrote a function for whatever reason. Somebody paid me a lot of money to write this function. What I have to do is be able to handle n number. It could be 1,000. It could be 1,000,000 documents, RSS feed documents. And the idea is to find out how many times a particular topic is found in all of those documents. So I wrote a function to do that. Now, when I'm looking to write code like this and I'm not exactly sure how to solve a problem, I'm going to just start drafting. Drafting code is what I want you to even think about. Because if you think about I'm writing a draft, then you don't have to worry about it being perfect right out of the box. And all I'm going to do is try to simplify this as much as possible. So I'm going to write this find function to use just one GoRoutine, one single GoRoutine to range over the documents. And then we'll see how well I did using one GoRoutine. It doesn't get any simpler than this. And I broke this into 4 stages. So we're going to be able to open up these files one at a time. We're going to read all of that information in. It's an XML document. I got to read it in anyway. Then we're going to decode that XML document into a piece of data that we can then search. So there it is. 1, 2, 3, 4 things we have to do for every document in order to find this found. And I've got a find function here. Now, we're going to simulate 1,000 documents on this run. I'm not going to pollute my repo with individually 1,000 documents. So we're going to pretend each one of these is a unique document. We're going to look for the term president, and we're going to see how this thing performs. All right, so let me save this. Let me go back to our terminal window, and I'm going to build it. And then all I'm going to do is I'm going to use the time command to get us a sense of how long this took. So if I'm looking at this number here from the time command, it took almost about 800 milliseconds to process 1,000 documents. Now, maybe that's OK, but I told you I want to be able to process 1,000,000 documents. And if we're close to like a second for every 1,000, this is probably not fast enough. All right, so now the idea is I have a working program. I can start trying to refactor and tweak this. So we've got 2 choices to try to figure out how to make this thing run faster. We can look at a profile, a CPU profile, and see if that shows us anything interesting. So why don't we do that first? So I'm going to go back into this code base here. I'm going to go to the top of main. And what I'm going to do is uncomment out these calls to pprof. What these calls to pprof are going to do is hook this program into the OS. And on a signal prof, we're going to be able to stop this program, get some program counters, and figure out what's going on in this program in terms of profiling. The thing is that in order to do that, every 10 milliseconds, this program is going to be stopped. All right, no problem. So we've done that. I'm going to write this out to standard out as well, just to keep my life simple. We're going to build it. I'm going to come back here. I'm going to use the time program. We're going to say, come on now. All right, let's do this again. It's called trace anyway, Bill. We're going to run the trace program, and I'm going to redirect to p.out. And you can see that this took a little bit longer to run. No big deal. What's more importantly is that we got this p.out file, which I have. OK, I want to start looking at the p.out file. So go tool pprof p.out. There we are. I'm in my interactive mode here. And I already have a function called find. So let's list find. And I'm going to bring this in a little bit. Find is going to find. There it is, our function right there at the top. And what we can see from find is out of the 600 milliseconds of cumulative time. So there's 2 columns here. There's the flat time and this cumulative time. That flat time is going to show me cost exactly on that line of code inside this function. You can see everything is cumulative. And if we look for the biggest numbers, we see that it's this open file that's costing us 540 of our 600 milliseconds. All right. So if I were to look at any other of those lines, that would really be wasting my time. So we can focus on open file. If I'm going to try to make this thing run faster, open file is going to be my problem. But I'm not seeing enough information about open file. So what I'm going to do is use the web call, open up a call graph, there it is, and try to see what's going on with open file. And basically, if I go to this really big box, open file is basically what the profiler is telling me is if I want to speed this program up, I need a new machine. Yeah, my operating system isn't functioning fast enough. So that's not going to happen right now, is it? So here's sometimes the problem with profiling. I love profiling. It can really help you find allocations. It can help you with levels of algorithm and efficiency. But this time, it's not really helping us. Right now, the idea of having to get a new machine doesn't work. So here's the problem. A profiler can only show you what is happening in your program. It can't show you what is not happening. And sometimes to speed up a program, it's about what is not happening, not what is. So in this particular case, profile didn't work. So our other option now is a trace. And what we can do is generate a trace down to the microsecond of this program, every function in and out. And maybe that will give us some clear indication of what we can do to possibly speed up this program. So let's exit the profiler right now. Let's go back into our code. And what we're going to do is open up a trace. All right. So this time I'm using the trace package from the standard library before I use pprof. And I'm going to say start a trace, write that to standard out, and then make sure that we stop that trace. All right. Let's save this file. Let's build it again. Let's go ahead now. We built it. We use the time program again. Trace greater than t.out, since this is a trace. There it is, 7,000 times. If you kind of look, our performance came back. Even though we're generating a lot of data, the program didn't have to stop for that. I now have a t.out file. There it is. And now I want to look at that t.out. So go tool, not pprof anymore, trace t.out. Now, this is going to bring up a browser-based UI. A couple things. One, this UI was stolen from the Chrome team for some other tooling. Look, these are back-end engineers. They're not front-end engineers. Two, there is zero documentation for what you're about to see. So many hours in airports and getting lucky every once in a while of finding someone who knew more than I did on the tool. And I would still say I only know maybe about 5% of what you're about to see here. All right? So just know some of that. I've also learned recently that it doesn't work in Firefox. So I'm wondering, Google Chrome stole from Chrome team. You get it? You might only be able to run this in Chrome. I don't know. I've been learning that lately. But I'm going to click on the View Trace button here, and we're going to see what we get. All right. So I don't know if any of you have ever seen this trace tool, but here it is. And I've got 8 virtual cores on my machine. You can see that 7 of them are in play here. You can see there's GoRoutine heap, thread information, GC. Let's just look at some of the basic information here on this trace. Now, we can see the number of GoRoutines, but I'm not that concerned about that. We know it's a single GoRoutine program. The heap is interesting. If you notice, there's 2 colors here. There's that orange and the green color. So the green is going to be our heap. You can see our heap starts basically at 0. It grows. If I click on that link right there, I can scroll this window up. So it's scrolling to about 4 gig. And then we can see that there's a GC that happens. We can see these blue lines in here, and a garbage collection happened. And when the garbage collection happened, the in-use or live heap went back down. We ran again until we got to about to that 4 meg, sorry. And then bop, the garbage collection happened again. So really not surprising, because what are we doing? We're opening up files. We're reading that into memory. We're processing it, and then we're just letting it go. So I don't really have a lot of permanent memory in this program, right? It's all really transient. So I'm not really shocked that we're seeing the live heap do that. So that's OK. Everything's good there. We can see a lot of garbage collection going on there, but really not so bad. And we can also see right in the beginning here. Here is that Go routine that we started. And I can even get a sense of what the stack trace does before we had that little, I don't know if I'd call it a context switch, but it was definitely stopped for a little bit and then started again. So we're running again there. These lines down here are going to be system calls we're making. I can click this arrow right here and select a bunch of these system calls that were being made and get more information about these system calls if that's important. But anytime you see anything underneath the Go routine, it means that it's, in these brown cases, we're doing these system calls. We could be doing other things as well. You could also see on proc 1 where we started the trace. So you can see the trace is running on a separate Go routine as well, and it was running on another thread there. What else do we see here really quick? Well, I see that in this garbage collection, let me move back into our tool there, that there is interesting gaps in time, isn't there? Interesting gaps in time when we look at that information. And we can also see that that Go routine, our main Go routine, is bouncing, right? From proc 0, bounces to proc 1, with some garbage collection stuff in between. And we can also see that near the end of this GC, the Go routine was asked to also help with some garbage collection on that mark assist. That's all pretty interesting stuff. We've got this down to the microsecond. But I'm trying to figure out what is causing or what can we do to make this program run any faster. And if I come back into this view real quick, I notice something from a macro view. It looks like the only code that's leveraging all of my CPU capacity is the garbage collector. I mean, if you just go down and look at the lines, it looks like we're just using one P, right, one thread at a time. But when the garbage collector kicks in at a nice uniform pace, it's using a lot more of my CPU capacity. So when we were looking at the profiler said, Bill, your system calls aren't fast enough. What the trace is basically showing us is we're not leveraging the full CPU capacity of this machine. And we knew that already. We wrote a very simple single Go routine find function. So what would be nice now is to try to throw some concurrency at this problem, right? Now, it's important to me to understand that when we talk about concurrency, I want you to think of concurrency as the idea of executing things out of order. I think it really helps your brain to understand that when we talk about concurrency, we're talking about out of order execution. And sometimes we want to throw concurrency at problems because it's fun or cool. But if you step back and go, wait, do I really want to do that out of order? Or can I do that out of order? It might cause you to just kind of hold back. Now, we can definitely execute this out of order. Do we care what file is being processed at any given time? Is there anything here constraining us to process one file before the other? No. This is a perfect out of order type of situation. And that's what we mean by out of order. Okay? So we've got a couple of options here. I like to keep it super simple first. We can always draft something and then refactor it, so I don't have to go after the most perfect solution. And the simplest way to probably throw more concurrency at this problem is to use a fan-out pattern. Now, I am telling you already, the fan-out pattern scares me a little bit because I told you we might want to process 1 million of these documents. And the idea of the fan-out pattern is, let's just throw a Go routine at every file. I don't care what order they get executed in. And maybe if we had about 50,000 files, I'd feel comfortable with the fan-out. And we're going to use a fan-out first because I want to code that just to see it. But I don't know if I want to throw 1 million Go routines at this problem, right? So what's nice is we can just build up the complexity a little bit at a time. So why don't we change this find function to use a fan-out pattern. We'll throw a Go routine at every file. We'll see how much performance we improve. We'll see what it takes to do that. Then we'll step back and go, great, but what happens if we have 1 million documents? Do we think this is going to scale? So let's go ahead and make some changes to our find function. So what do we know right away? We know that we want the number of Go routines to be a length of docs, right? So depending on the number of docs is the number of Go routines we're going to need. Now, we also have an orchestration problem. But here's another thing. You've got to recognize when you have a synchronization problem and an orchestration problem. A synchronization problem is when you have to get in line. You get to all the go-routines, get in line and take a turn. That's a synchronization problem. The orchestration problem is when two go-routines have to talk to each other. That's an orchestration problem. These are two separate situations. And traditionally, the channel is there for orchestration. You could do some synchronization with channels. I tend to stay away from it. There's always exceptions to every rule. Your mutexes and your atomic instructions are perfect for the synchronization. So I really have an orchestration problem here because this find function cannot return until all the files have been processed. We kind of have to wait for that. And wait groups are really good for orchestration. And I find that a lot of developers up front feel like if they're using wait groups, they're doing something childish or something, not as technical. Like, that's crazy. Like, wait groups are simple when we don't need to get information back from go routines. We just have to know when they're done. I use wait groups all the time. I love them, but I'm going after simplicity anyway. So here we go. We're going to add G to our wait group. We're going to say there's going to be G number of go routines that we're going to deal with, and we don't want to leave until they all report that they're done. So I've set up some of our orchestration yet, but I'm not really done yet. We still haven't created these go routines. We do know, though, because we have this piece of code already, and we have the 4 steps, that whatever it is we're going to do, we've got to wrap every one of these lines here in a go routine. So why don't we just set that up without knowing too much? Yeah, I got to deal with some better error handling, but we'll do that in another revision of this code. Notice how vet is complaining to me immediately here in the editor, because it's found a closure bug. Because right now we're closing on this doc variable, which is not good. So we're going to have to pass that in. Thank you, vet, for finding that for me. We know that's going to have to happen. So now we have a go routine. We haven't finished our orchestration yet. So let's just put the done in there. So I've got my orchestration in. I've got my go routines in. Each one is going to process its own file. There really are 2 more, well, there's one major bug here and one minor mechanical sympathy problem here. The bug that we have is on lines 89 and 94. I've got a data race here. I've got 8 potential go routines trying to do a plus plus on the same memory location at the same time. I've got to synchronize that. Only one go routine can do that at a time. I have a synchronization problem. So how do we solve this? Well, since this is only a word of data, what we can use is the atomic instructions. Now, it wants a precision-based integer. So we're going to have to fix that for a second. But we can at least lay this in. We can say, no problem. I know you want this to be in 32. And we're going to have to convert this back. Now, technically, we're done. I mean, this code will work. But I am still a little concerned about what's happening on line 90. Now, don't have a lot of time to go into it, but we do have a cache coherency problem here. My machine has 4 cores on it, and each core has its own L1 and L2 cache. And if we think about this really quick, and if you were in my class yesterday, you'll have a better understanding of what I mean. Every time a go routine wants to increment that line 90 or 95, the cache line for found has to be brought into that core, right? And I'm going to have 2 coroutines executing per core, which means I'm going to have 4 copies of the found variable inside my hardware. You know what happens now? This is really scary, actually. So let's say the go routine on core 1 wants to do the found plus plus on line 90. Now what happens is the hardware has got to go and say, hey, is this found variable also in those other 3 cores that you have? And they're going to go, yeah, I've got it. Well, guess what? Your copy's no longer valid because I've just updated mine. So now when you want to go do a plus plus on your copy, sorry, you got to go get a new copy. That could cost you 100 clock cycles. Like, that's super expensive. So what we got right now is a problem, the cache coherency problem, where every time we do a plus plus, even though it's synchronized, we are going to be thrashing memory. Because every core is going to have to say, nope, my version of that copy of found is dirty. Go get another one. Go get another one. Go get another one. Now, over 1,000 files, you probably won't feel it. We get to 1,000,000 files, we're going to start feeling it. So this is one of those things where if we throw more power at the problem, this is where I get scared when somebody says, well, I got a 32-core processor. I go, you better know what you're doing with it. Because imagine this on a 32-core processor or on a machine with multiple physical processors. Like, electrons have to go across some bus to talk to these processors. Like, this isn't free. So the cache coherency problems are interesting, and we've got to deal with that a little bit. So one way to deal with this is to use local memory. In other words, we know that we don't know how many times this found plus plus is going to happen for any given document. We know right now that we find it 7,000 times over 1,000 documents. But if we do something like this, let's use a precision-based integer, then what gets interesting is as each go-routine is doing their own local count, if they do it on their own local variable, you know what happens? The cache line for this local variable isn't going to be the same as another go-routine's local variable. So what we just did is get rid of all of that memory thrashing, because the plus plus is happening on its own unique cache line of memory. Now that being said, actually the other cool benefit too is I don't need the atomic instructions here, do I? I don't have a synchronization problem anymore, and I reduce some of that memory thrashing. However, I got to write lfound back to our global, and we know that's going to happen n documents. So we're going to have to deal with that too. But let's do this. Let's come back into this defer, and we'll do our atomic stuff here. And in 32, address found, lfound. Oh, we're going to have to move that variable up, won't we? So let's do that. We'll move this variable up. And now what we end up doing here is pretty cool. We've minimized, haven't truly eliminated, but we've minimized some of our cache coherency problems by at least making sure that the bulk of the plus pluses are happening on our own cache line. They're not atomic. We're not going to get hurt too bad on synchronization. We're not going to thrash memory. The only time we're going to thrash some memory is right there on line 67. And unfortunately, that is 1 per file. But guess what? We've just implemented a fan-out pattern here. We're now going to have an out-of-order type of algorithm to process all of these files. So let's do the following here. Let's kill this. Let's build it. And let's run it again. Now, luckily I didn't make a mistake because we found it 7,000 times again. Yay. But notice we went from almost 900 milliseconds to 200 milliseconds. That's pretty cool. So I'm feeling pretty good about this. But let's take a look at the trace for this piece of code here. Go tool trace t.out. All right. So that's a much nicer trace, isn't it? I mean, I'm using my full CPU capacity now. Let's inspect a few things that you see. Notice that we've got this large peak of go routines up and go routines down. What's happening? First thing you got to understand is the trace is only going to show you go routines that are in an executing or runnable state. When go routines go into a waiting state, they tend to just be hidden because they're not really in play. And remember, we created 1,000 go routines here. If I try to select the top of this thing, if I can do that, it's not letting me. There we go, I got a selection there. I mean, we could see that we had, in that moment in time, 897 runnable and the 8 running, which we would expect. But suddenly, it just kind of drops off. And it's not dropping off because we've finished all of that work. I mean, look at what's happening right here inside this trace. It's super interesting. Notice that we've got these long time slices, which we would expect to have. These first few go routines that get selected are working. And then we get inside of our first garbage collection. And when we get inside our first garbage collection, what do you see? a lot of tiny context switches. Suddenly, the bulk of those go routines are being started and then basically placed into these waiting states. And as they get started and placed into waiting states, we see that line go down. Let's look at a little bit of what's happening in here. So I'm going to bring this more into view. And let's just select one of these go routines. I think you're going to find this super interesting. This is the stack trace before it got stopped. And if you notice, there's a call to Malloc Gc. Malloc Gc is the call to allocate memory on the heap. So think about how smart the scheduler is here. It's in the middle of a garbage collection. This go routine says, I need some memory on the heap. And what does the scheduler say? Whoa, slow down there. I'm doing garbage collection. And I've got other go routines that don't need the heap. So guess what? Stop. And I'm going to bring somebody else in that I can run concurrently while we're working on the heap. How cool is that? The scheduler is ridiculously intelligent. It knows what these go routines are doing. And it can make very smart scheduling decisions. And we're seeing it right here. If we were to look at every one of these go routines before they stop, you'll see that they're all, at some point, trying to make that Malloc Gc call. And so we got a lot of concurrent work done in the middle of this GC. Even though it looks like this was a very long GC, remember, we're still getting a lot of concurrent work done. The idea is to get as much throughput through that while the garbage collection is running, and we're doing it. And then near the end, we start to have these longer time slices again. And now that there's less go routines in a runnable state, okay, things kind of mellow out again. Now here's something that's kind of cool. There's a lot of chaos, it looks like, going on in here, right? But what if I wanted to see those points where the garbage collection really is involved? Maybe I want to see the mark-related stuff. I can start filtering out this graph, and I don't see any color on that. There it is. There's some color. So if you could see here, again, we've got some go routines doing some mark assist. What if I want to see some things that we know are specific to stop the world related stuff? There's one down here, some sweep termination there. So I can start filtering out the things that we know are garbage collection specific. And if you really notice that these go routines are running concurrently, they may be assisting the garbage collector in time, but we are getting work done. OK, pretty cool. Except, even though this works, what happens if I throw 1 million files at this problem? I am scared out of my mind to throw 1 million go routines at this thing. I'm not saying Go couldn't do it, but that's a tremendous amount of load on the scheduler. What I'd rather have is something a little bit more consistent, no matter what number of documents that we're processing. And so what could be interesting here is, instead of creating a go routine for every file, what if we create a go routine just for every virtual core that I have on the machine? Then whether I'm doing 1,000 or 1 million, we'll just leverage 8 go routines to do it. And when garbage collection is coming on, maybe we'll even get some of those GCs done a little bit faster. They still might even be able to assist. Everything should still be fairly concurrent. And maybe we'll go a little faster as well. So just to look at our time on that last one, which was 288, right? So how do we do this? I mean, what we're basically saying now is G isn't length docs. It's runtime.num CPU. This is now the number of go routines we want. But if this is the number of go routines we want, we have to have a way of feeding these go routines all of the work. So we could use this concurrency pattern. What we can say is, why don't we build a channel here that can handle all of the work up front, length docs. What if we feed this channel all of the work out of the box? And what if we close this channel immediately? Think about what we just did here. Since we have a well-defined amount of work, we know how much work we want to do. We know how many go routines that we want to do that work. And we're doing it based on mechanical sympathy, based on how many virtual cores that I have. So you may have less go routines than I do, or more if you're lucky, because of your hardware. We don't want more go routines than we have cores. It probably won't really make it run any faster. And so we take a channel of a well-defined size, we fill it up with the well-defined amount of work, and we close it because that way when all of the data is flushed out of this channel, we can then signal to shut this program down. Which now means that this for loop here has to be based on the number of go routines. So we could just say, go from I equals 0, I less than g, I plus plus. And we now are only going to have the 8 go routines here. But in order to process this, we have to feed off the channel. So we can range off that channel. We can use our closures again. And we got to get to the bottom of this thing right here. And obviously, we're not passing in docs anymore. So that's interesting. And now every one of these 8 go routines is sitting here trying to feed data off the channel. Once there's no more docs, that for loop will terminate. You know what's also really cool? The bulk of the counting is now happening on the local variable, right? Like all of it is basically now happening on the local variable because we have 8 virtual cores, 8 go routines, each incrementing their own local counter. We're no longer running into those cache coherency problems. And at the end of the program, we only have to deal with this now how many times? Like 8. Yeah. So all of those other mechanical sympathies, that could save us too on a little bit of performance on very large numbers of documents. All right. Let's see what this looks like. Feeling pretty good about this solution here. OK, let's build it. Let's run it. We were at 288. We're now at 265. I saved like another 20 milliseconds off the time. Yeah, that's pretty cool. We don't have a huge amount of complexity here either. I want you to understand how we got to where we are. I mean, we've been drafting code from the beginning. We knew the last solution wasn't the perfect one, but we knew it was a good step to start at to then get to maybe the right solution. Now, you guys don't really care about the trace, right? You don't want to see it. Yeah, I know. Here we go. So let's take a look at the trace for this program. I mean, hopefully it doesn't look much different. And it really doesn't. But if you really look at the GCs, I mean, we come back here. I do feel like this program, the new one, looks a lot more kind of stable and consistent, doesn't it? Yeah, I think it does. And you see we're still using the full breadth of our CPU. Now, this is all great. But what if out of these 1,000 files that we're processing, our real performance problem right now is 1 or 2 of them? Like, right? Maybe there's 1 or 2 outliers that are really causing us our pain. It would be nice to try to find those, wouldn't it? It would be nice to get this trace down to the file level, wouldn't it? In 1.11, we can do that now. Very cool stuff they've added to the trace API. So why don't we do that in the last 10 minutes that we have here? So here's the idea. Every time we process a file, I want to create a new task. And what the task will let me do is generate specific file level trace information. So let's use the background. Context.background. I don't know why you're doing that, so I'm doing something wrong there, but we'll figure it out in a second. And what we'll do is use the document. Now, new task is going to return 2 things, a new context and a task. So context, task, there we are. Brilliant. Now, I know I did something wrong here. So, oh, we haven't used it yet. Fine. So now that we have a task, let's start adding some regions. So trace dot start region. Now, the start region wants that context we just got out of the task, and it gives it a name. So what do we want to name this? Why don't we just name it exactly what we're doing? And this is going to return a region. So here we are. Here's our region. There we go. Now, all we have to do here is region.end, and we've just created that region right there. Now, what's nice about this is the code behind these calls shouldn't be bothering you in production. There's like conditional logic here that says don't do the massive amount of work this does unless a trace is actually running. So you could leave this in your production code in those special places that are important to you, and it should not affect your performance. All right, let's add that region. And now we're going to add our search region. Let's do that. And then we've got to end that task. So task.end. Brilliant. This is compiling, so life is good. So I've just added a new task per file and a region for each step in this process. Good. Let's save it. Let's kill this. Let's build it. Let's run it. Beautiful. Still 7,000 times. You see our performance really didn't even degrade. Oh, now we got to run this. Go. Tool trace t.out. Boom. There we are. Now, if you notice, I've got two links at the bottom. User-defined tasks. So let's click on user-defined tasks. And now, what do you see? A really beautiful HTML-based table. I didn't write the UI, but it's functional. But what you see is every file that we processed and how long it took. Now, this one's interesting right here, right? This one took a long time. Maybe there's something special about this file right here. Maybe not. But we know it's the same file, right? But I can click on this link and get this information right here, which is breaking down what happened in this trace, the elapsed time. Okay, you can see that in milliseconds. We could see the search took 7.1 milliseconds, basically. But if you notice down here, there was like a full second of garbage collection that happened when we were processing. All right, it would be nice to kind of see more details, right? Let's click on this task 13 link. Boom. There it is. So that's where we were in the trace when we processed that file. And we could see that two garbage collections happened to fall within that span when we were processing this file. But this might be a file you want to, in a real-world situation, take a closer look at and maybe isolate in a specific benchmark to see if there's something special about that file. But how cool is this, man? This is one of the most beautiful things about Go for me. I've worked in a lot of other programming languages, and we just never had this tooling unless you paid a lot of money for it. And even then, we didn't have this tooling. And what's brilliant about the tooling, at least for me, is when I'm writing code, I don't stress out anymore if the code is fast enough, if it's going to be something I can put in production right away. I really do put into my head every day, this is draft, this is a draft, this is a draft piece of code. Great, I've got a draft piece of code working. What do? Let's review it. Let's refactor it. Let's see if we can make it better. And there's zero stress about it because I got the tooling here that's going to tell me. So I don't have to try to guess during coding. I just get something to work, we throw it up here, and then we find those problems. But I also want to stress that I knew when I wrote the fan out that that wasn't going to be my final solution. But I knew it was the simplest thing to code next. So I put it together. But if you notice, when we went from the fan out to that 8 go routine solution, right, where we use the channel, was there much of a lift going from there to the next step? No, there wasn't. There wasn't much of a lift to get to the next step. So I'm seeing this a lot. I want everybody to really appreciate the tools here, but appreciate the tools to the point where you don't feel like you have to be perfect every single time you sit at your desk. Don't. Draft as much code as you can. Prototype, and then let the tooling show you what's going on. All right, guys. Have a great conference today. If you have any questions, find me during breaks, and I'll show you stuff. It's all in the repo. You can do this stuff yourself. Thank you. Good morning.